Alina talked about how to collapse 100,000 trials into one. It's very good. It's important. So I'm going to talk about a different aspect. So supposing that we have already gathered exploration data, how can we best use it? By the way, I saw a really inspiring talk recently at so there's this KDD conference, which is one of the machine learning conferences, and David Hauser talked. He's one of the guys who worked on the Human Genome Project, and it started kind of slow. There's all this complexity about the details of biology, and at the end you realize he's talking about curing cancer, and he was serious about it. Cancer is a complex disease where it seems that we really need to do some serious data stuff in order to succeed. Okay, so I'm gonna refresh a little bit. So we're thinking about situations where, in the medical domain, where a patient comes to a doctor, and then we want to come up with a treatment, and then the patient's going to respond to it. And the goal is to, so the formalization of this is this setting, this contextual bandit setting, where we see features, we take an action, and then we get some reward for that action. Okay, and our goal is to learn a good policy for step 2. Okay, so I'm going to go through 3 scenarios where we can try to use exploration data in ways that you may not be familiar with. So the first scenario is the failed study. So somebody has a new wonder drug, and they're like, this is going to cure cancer, and so that they have a trial, and the trial fails. Right? That happens. And then the question is, what can you do? So if you look through the data, you might discover that the drug did have an effect. It's just that it helped some patients and it hurt others, right? And so you can go, that's interesting. And now we would like to use this existing trial information to try to come up with a new policy, something different from what the trial was studying, which maybe will actually succeed. Right, so the way to do this is based upon this importance weighting trick that Alina just mentioned. So we have a policy. The policy maps features to actions. And I'm going to talk just about how we evaluate a policy and not yet about how we learn it. Because it turns out that being able to tell if a policy is doing something good based upon exploration data is like 90% of the way to actually being able to optimize over a set of policies. Okay, so we have some previous trial which collected exploration information. And exploration information has this form. We have some features. There is some action that was taken. There is some reward that was observed. And critically, we have some probability that action was taken. Right? So it's important to log that. Sometimes, so I'm at Yahoo, and sometimes I forget to log that. Okay, so now if we want to evaluate a policy, we can try to give it a value. And the value would be, this is the empirical expectation over our samples of the reward divided by the probability times the indicator function. So this is 1 if the policy chooses the action and is 0 otherwise. Okay, so this is a really critical equation to understand. It's so critical that you should just memorize the proof of it. Because if you're going to be working with exploration data, if you don't know this, you don't understand it well, then I don't know how you can succeed. Okay, so the claim is for any policy, for any distribution which generates the features and the rewards, the value of pi is an unbiased estimate. And it has deviations which are bounded by 1 over the square root of t times the minimum probability. Okay, so if the probability becomes, this is a little bit tricky because it's in the denominator. So if the probability becomes small, then t times the probability becomes small. And then 1 over that becomes large, like 1. Once you get up to 1, we're imagining, by the way, that the rewards are, it's important to think about the rewards in a normalized sense. So they're bounded in a 0-1 interval. You can, of course, shift and rescale and whatnot to achieve that kind of thing. Okay, so you want the deviations to be small, which means you want either t to be large and P to be large, oops, or preferably both, so that the multiplication is actually large. Okay, so the first part of this, the unbiasedness, is proved right down here. So I'm actually going to go through a proof here, which is a little bit unusual perhaps, but this is really critical. You have to understand this in order to understand how you can learn from exploration. So we're looking at, it seems like it's a little bit dangerous to use the mouse. Let's try. Okay, so we're looking at the expectation. So we're going to fix everything except for the action. So we have a fixed policy. We have a fixed context. We have a fixed distribution over actions. And we have a fixed reward vector. Okay? And now the only thing which is varying is the action that is actually chosen. So we're taking the expectation of the reward divided by indicator function of policy equals action, and then dividing that by the probability of the action. Okay, so the expectation is really a sum of the probability of the action, and then we have some cancellation because we have the probability of the action divided by the probability of the action. So it's going to cancel out, and then you have an indicator function which is only going to be 1 for one term in the sum. So the only thing that survives is this one term in the sum. It's the actual reward of the policy. Right? So that's the critical thing. And then, of course, you can take an expectation over x and over the reward vector given x, and then you get the full result. Okay, so this is a very critical equation. And this is the first trick. So this is, if you can find a good policy, a policy which has a large reward according to this estimator, then maybe you can actually create a new trial based on that policy, which will succeed. Okay, so the next scenario is exploration scavenging. So this is a different sort of thing. Different countries, for example, have different ways of treating patients. It could actually be different in different states too, or even different hospitals. But nevertheless, we'll use France and the U.S. So maybe the French treat broken legs a little bit differently than the U.S. And you would like to know, do the French do it better, or does the U.S. do it better, right? And okay, it's a natural question. It's generally delicate to try to extract causative information. Is the treatment causing a better response in France than in the U.S.? But nevertheless, there's some observations. So there's some people who travel between France and the U.S., and so they occasionally break a leg, and then they get a treatment in whatever country they happen to be in at the time, right? So there is some exploration going on here, but it's not like a randomized clinical trial. It's not nearly as clean, right? So now the question is, what can we do, right? So we would like to be able to use this kind of natural, uncontrolled exploration in order to at least get some estimate about whether or not it's interesting, the French way of doing things, right? Okay, so what can we do? So we have to make assumptions to proceed. We have to assume that the travelers who go between France and the U.S. are kind of typical of the overall populations. We have to assume that leg breaks in France are kind of like leg breaks in the U.S. And these assumptions are necessary, right? So we have to make them in order to proceed because we have uncontrolled exploration, and we should be explicit about them because the analysis will rise and fall on this. Yes. Didn't quite follow that. Yeah, so people can come up with, so the critics can come up with criticisms of the sort, well, the people who go between the U.S. and France are typically wealthier, and therefore they're more healthy. And so the way they respond to a treatment may be atypical of the population because they're already healthier. Okay. Right. Yeah.
Why isn't that a giant randomized trial?
Okay, so right. So then there's questions about how the lifestyle of the French differ from the lifestyle of the U.S. and so forth. Yeah, they may be different in some way. So I'm trying to extract a population which we can argue is essentially the same, right? And the population which we can argue is essentially the same is the set of people who travel in between the U.S. and France, right? And of course, this will be a smaller subpopulation, but we can be more sure that there's less bias, right? What's that? So we have to be very careful. So this is not the kind of analysis which is going to say, oh, we should use the French way of doing things. This is the kind of analysis which is going to suggest that we should do a study of the French way of doing things. Sure. So, this is the example that I came up with, but you can freely insert whatever examples you want. I'm sure there are examples of this sort, of this general style, which are important. Okay, so okay, okay, so the key trick here is to learn a predictor of the probability that that you observe the action given the features, right? So you have some features related to the person. Now you want to predict whether or not they're going to be treated in the France or the U.S. And then we can define a new estimator similar to the old one, where we just kind of pretend that the probability is this predicted probability. And because this is a predicted probability, it can be wrong, right? So in particular, if it goes to 0, then you're going to have some serious problems. So the way to deal with that is you just make it not go to 0. Okay, so it's a simple trick. And now it's going to introduce some bias, and we need to think a little bit about. So there's two things we need to think about. One of them is how much does the bias of introducing this tau affect us, and the other one is how much do the errors in our estimates of p hat affect us, right? So p hat is not going to be a true p. Since you're estimating, there will be some errors, and it's important to know how it's going to affect us. Okay, so what you can prove is that for any distribution, for any pulse that you want to evaluate, so value of pi is a true value. You're going to be off. Okay, so first of all, I'm going to assume for the moment that the true p is greater than tau. The true probability of the traveler being in France is greater than tau. Okay, so then what happens is the square root of the regret. So we're going to measure how badly our p hat errs from our p according to squared loss. And the square root of this quantity here divided by tau kind of lower bounds our empirical expectation and also upper bounds if we add it, right? Okay, now we need to think for a moment about what happens if the true p is less than tau. And the answer is, essentially, we underestimate the value of the policy. Okay, so if you're going to have bias, there's two ways you could have bias. You could underestimate the value of a policy, or you could overestimate the value of a policy. And being a conservative, I guess I prefer underestimating the value of the policy to overestimating. Okay, so this is a way to use uncontrolled exploration that you happen to find in the environment. Right? And anywhere you can find uncontrolled exploration, it's appealing to start asking these kinds of questions. It's because this gives you access to much more data than you might otherwise have access to. Okay, so Are there questions about either of these first two tricks? So importance weighting trick, extremely important. It's fundamental. Exploration scavenging is very interesting. We actually have used this a little bit at Yahoo, and it appears to do useful things. It is often the case that they forget to record the probability. So the reason why this comes up at Yahoo is Yahoo and a lot of internet companies make money from advertisements. And advertisement setting, a user comes to a web page and you want to display an advertisement, and then if it gets clicked on, maybe Yahoo makes the money, and if it doesn't, then Yahoo doesn't. But critically, you do not learn about what would have happened if you displayed other advertisements. Exactly the same problem. This is the fundamental problem. It comes up all over the place. It's in the medical domain. It's in the internet advertising domain. It's just a property of the world that we cannot reset time and try out other things. And so we need to solve these problems well. Okay. So now I'm going to talk about one more thing, which is studying similar things. So some drug was studied, and it was found to be beneficial with predictable benefits. And then, they had a patent on it, and the patent started to wear out, and then they're like, we want a new drug with we can patent. And so we're going to create a new drug, which is very similar structurally to the first drug. I think this actually does happen, and likely has very similar benefits. Okay, so now, hopefully that's true. I don't know. The patent games get a little bit confusing, but hopefully the goal here is to actually create something similar. And now the question is, can you get away with a smaller study for the new drug? Because the first study for drug A was going to be very expensive and involve a lot of exploration. And now, because we know the benefit profile of drug A, and we suspect that's similar to drug B, can we safely use that information in some manner in order to minimize the cost of exploration the second time around? Right? And the answer turns out to be yes. This is something I learned about relatively recently. There's a technique from statistics called double robust estimation, which is applicable here. So if you have a reward estimate, any reward estimate, so this reward estimate can come out of thin air. It could be always 0, in which case you end up just getting the importance weighted estimator that I discussed before. But if you have a reward estimator, then you can modify your estimator of the value of a policy in this way. You can say, well, I have the true reward that I observed. I'm going to subtract off my estimator, and then I multiply by the indicator function and divide by the probability, and then I always add in the reward estimate. Okay, and then the empirical expectation version of this is right here. So that's a trick. It's kind of strange looking. The claim is we have not violated the soundness. Okay, so there's several claims here. One of them is we can still prove high probability guarantees just as we could before. And the other one is this actually does help. If your reward estimate is even remotely accurate, this helps, and it can help substantially. So one way to look at this is to just think about what happens with the deviations. So here I put in a p hat because you can also, of course, use this trick with the probability estimation. But of course, if you have the true p, then you would plug that in instead of the p hat. Okay, so big delta will be the difference between the estimated reward and the expected true reward. Okay, so that's how much our hat screws up, right? And then little delta will be it's a measure of the error of p hat. So it's a slightly different measure from before. And the reason why is p hat's in the denominator. So you really care about kind of the ratio of p to p hat. So we have a ratio here. But if p was actually p hat, then the ratio would be 1. So you really want to care about the difference from 1, which is this 1 minus p over p hat. Right? But now, so the little delta is the error in a probability estimate. And then we can prove a theorem. We can prove that for all policies and all values of x and r vector, so all distributions over x and r vector as well, the double robust value estimate minus the truth is bounded by the error in delta times the error in little delta. So this is, you think about this for a minute. So suppose that p hat was p, then little delta would be 0, and you know we'd succeed. This is unbiased, just as we were unbiased before. So we threw in the reward estimator in a manner which did not cause bias. Okay, so that's interesting. Another thing to think about is what happens if your p hat estimate was terrible, right? You were doing some sort of uncontrolled exploration experiment and you're just kind of all over the place. But your reward estimate was good. So in particular, if your reward estimate had 0 error, then this quantity would also be 0. So there's 2 ways to be right here. One of them is estimating r hat correctly. The other one is estimating p hat correctly. And these things multiply. So we're thinking about values of big delta and little delta, which are typically less than 1. If you multiply 2 numbers which are less than 1 together, you get a smaller number, and your errors get smaller. So you can prove some more things. You can prove that this actually improves the variance as well. And that, of course, drives deviation bounds, and that tightens all of your exploration techniques, which Alina just talked about. Okay, so we did some experiments with this. We were kind of excited about it, but this is not related to the medical domain. This is just related to machine learning. So in machine learning, we have various data sets. Unfortunately, they're not exploration data sets because it's pretty hard to get a hold of exploration information, as was discussed earlier today. But there's a trick. You can take an existing labeled data set and you can manufacture an exploration data set, which is quasi-interesting. The ways you do it is, so we have a bunch of data sets where, you know, given these features, the label is this value, right? So that's providing information about all of the actions. But we can pretend that we actually have information about only one of the actions by randomly checking one of the actions and seeing what the loss of that action is, right? So we can check a random action and we can get the loss of that action. And maybe we just do things uniform randomly, so p is a very simple quantity. And then we can learn a reward estimator using whatever technique we want. I think we did linear regression. And then you can create a double robust estimator for each of the actions. Right? So for each action, we can plug into this formula here and get an estimate of the value of that action. And then we can learn a classifier which takes into account the varying costs of the different actions. And it turns out this works pretty well. So if you can of course use that classifier with the exact same approach when r hat is always 0. So that's just the importance weighting approach that I talked about at the beginning. And then you can try to learn your classifier. And it turns out that it works not very well. So that's the red. So we're looking at error rate of the classifier on a test set, which is actually labeled. So we're pretty confident that we know what the right answer is. And the error rate is large for the importance weighting trick. There's also an algorithm called the offset tree that we worked on, which tries to directly use exploration information. So it takes XARP quads directly as input. And so that's the blue. That works pretty well. And the latest thing is this double robust approach, which is the green. And the green actually tends to work better. So that's kind of surprising because it says that we're really reducing the variance of our estimates in a way which really matters for the purpose of learning a good policy. So these are the scenarios. If you have a failed study, you can do offline learning and evaluation of new policies based upon this exploration information. So the data from a failed study is actually of great value. If you have large databases of how people are treated in different locations, you can try to do exploration scavenging. And if you can come up with any kind of even vaguely sane reward estimate, you can improve all of the above, including all of what Alina talked about as well. Well, all of the confidence-bound related approaches that Alina talked about as well. Okay, so I have a bibliography here, which has some recent papers, and then, of course, in these papers, there's lots of other pointers. There's a tutorial that Alina and I did on exploration and learning. So it goes into substantially more detail than I think is appropriate here. But if you're interested in it, I think that's a good place to look at. And then there's also some further discussion on hunch.net, which is a machine learning theory blog that I run. Okay. Other questions? Yeah?
I follow the logic of what you're saying in some of the mathematical. I think there are a lot of other problems with clinical trials, clinical studies, that you might want to select other examples than clinical trials. The reason clinical trials fail most commonly is due to factors that don't always show up in the observations.
Mm-hmm.
And I think part of what you're trying to pull out is from the observations, how to improve the trial. And so I think because of the context of the trial, the factors that are involved in the approach in the design of the trial, it may not be the best example to do. Not that what you're doing isn't correct, because that's not. I just think either you need to add a lot of contextual information to know what the limitations are because of that contextual information. Because we deal with the pharma side, we deal with the regulatory side. And both of them would have some significant opposition to only the refinements that you're making. Not that they're not correct, it's just there are a lot of other business considerations
Yeah.
that enter into it.
So we've had some discussions with other people about this, and there are enormous problems with changing the way that clinical studies are done. One thing that we can contribute is approaches which are as mathematically rigorous and plausibly substantially better than existing approaches, but you know there are large obstacles. Another part of why we've focused on clinical studies is because that is the form of high-quality exploration data that I'm aware of in the medical domain. If there's other forms of high-quality exploration data, then, of course, all these techniques apply there as well, and plausibly they should be used. So there are very big problems because there's a lot of money involved, basically, and that makes some people, you know, act according to their paycheck. Yeah.
How do these methods hold up, or how do you adapt them? One of the presuppositions which I have is that you've got a problem, you pick a treatment, and then you look at the reward for that. In medicine, it's not uncommon for us to blanket these treatments and hope that the rewards we're looking for happens, and then which of those would be useful? So how do you accommodate that concept?
Okay, so this is called a credit assignment problem. And in general, credit assignment is pretty hard, actually. So the credit assignment is kind of orthogonal to what I'm talking about. One method that people use for credit assignment comes from sort of these lasso or compressed sensing type approaches. So the idea is you hypothesize that it's only one of the n things which actually matter. And then it turns out, okay, so let's suppose that the world was very nice to us. You had n patients, each of which you gave n simultaneous treatments to, and only one of the treatments, all the patients responded, in exactly the same way, and only one of the treatments actually mattered, right? So then, you could start to use these. Well, I guess you actually need to be varying the treatments. Maybe you vary the treatment. You choose a random subset of the treatments on each patient.
We do vary the treatments.
Yeah. Okay. So we choose a random subset of the treatments on each patient, but maybe it's a subset of size n over 2. Then the claim, I guess, would be that after just seeing log n patients, you could start to recover the thing which was actually working. But that's a special case. That's when there's only one of the treatments that's doing something. If there's a combination, then it becomes more difficult. In general, it becomes like k log n, where k is the number of things which are actually important. So it's a different subject. It's a lot of depth there. Yeah?
Well, I think the theoretical results are very nice. If I was to play devil's advocate, using Alina's example, so let's say I'm talking about trying to choose treatments, which eventually will be applied to many people. I would be willing to spend 1 billion hours of CPU time to design this strategy. Are you sure that your algorithm will use a better strategy than you by some approximately optimal Bayesian method using 1 billion hours of CPU time?
So one thing which is important is that Bayesian methods are not actually incompatible with what we're talking about. We're talking about a method for evaluating policies. Any particular element that you have a prior over in your Bayesian method is going to be a policy or imply a policy. And so you can apply this to whatever set of policies that you're thinking about.
Policy optimization algorithm.
Yeah.
Proposing that this is my positioning strategy.
Yeah. So there's another thing which I think is very important, which is it's actually related to Alina's talk. So you can find that. It's up here. So if we go back here, so if you think of clinical trials as sort of the gold standard, the EXP4P analysis is like a platinum standard. It works in a much more general setting than we're describing with this theorem. It works even if the rewards are chosen adversarially and the contexts are chosen adversarially, which is kind of shocking. But it's not impossible because we're just competing with the best in the set. And furthermore, the individual things in the set are not fixed policies. They can just kind of vary their actions on a per round basis arbitrarily. So what that means is that one of the experts in the EXP4P setting could be your Bayesian system. And if it performed better than other approaches to doing treatments, it would win under this regime, without a doubt. So there's even stronger standards of success, which are greater than the gold standard of clinical trials, right? And maybe that's interesting too. I don't expect those to be adopted because, well, it's an entirely different bit of math. But oh yes, yeah. Oh, okay. So let me mention constants here. So the constant on EXP4 is 7. The constant on policy elimination is, I think it's also 7. All these are small problem-independent constants for all the algorithms that we've talked about. Now, that's not to say that there isn't a concern there. I think that even if the constant was 1, you'd still want to crank on we're using sort of exponential moment method, large deviation bounds in order to prove these things, right? And those are not perfectly tight. They're pretty close to about as tight as you get. They have the form of the central limit theorem if you look at them, but they're not as tight as you could possibly get. So it's plausible that before this kind of approach could be applied in a medical trial, you'd want to crank on it, right? You want to get everything down to a binomial distribution. to tighten up the confidence intervals and reduce the sample complexity required, right? So it's much more important to minimize exploration when there's people involved than it is when there's an ad involved. Yeah?
What prevents the standard from square root of t is so what can you give me a sense of like if you were to be incorporated, like what's preventing you from that strategy?
I think I can't really answer it. So, there's these things which, once you understand the math, seem kind of blindingly obvious, like you should be doing, and why isn't it being done? I don't know. I can tell you why it's blindingly obvious. It's just, let's see, it's in this proof right here. So, if you explore first and then you exploit, then you're going to have some regret associated with however much you explore right there. And then you're going to have some regret associated with the fact that you don't really know everything, right, over the remaining rounds, right? And then if you just optimize tau, you end up getting t to the 2/3. And typically, I think we don't even optimize tau, but, if you optimize tau, it'd still be t to the 2/3. Yeah?
These are mathematically elegant and perhaps obvious solutions to complex problems, hypothetical solutions to complex problems. Have you attempted to look at not perhaps the perfect data sets you talked about that were generated in the trials, but perhaps the data generated from the early routine clinical practice? You have a large enough data set with large enough populations and large enough interventions.
Yeah.
It's a test bed to find out if this works.
That's right.
Because we know the outcomes, given sufficient time.
Yeah.
Have you attempted to use those data to demonstrate the blindingly obvious mathematical value?
I have not. I mean, we've been mostly focusing on figuring these things out, the math, rather than applying it.
The convincing statement is the math presents what sounds like a highly plausible theory. And we test the theory against real data. So the question is, what adverse events support right? What you're not in the market and docs are giving you all that real stuff like that. And then you get your adverse events coming in. And then how does that affect the variance on the next findings that we need to discuss to be able to say how you're going to extend that?
Yeah. You're thinking about the double robust approach.
How do you come in the back end? When the question how do you come in the back end into the practice and what farmers are interested in adverse events on their drug within practice.
Yeah.
Requirement to be able to make.
Yeah.
So how do those data points get treated in the back end and come up further assumptions?
Yeah. I don't really know enough.
It's important to figure out.
It's important to figure. I hope this gets figured out.
Let's just say you make a mistake from my aggregate, right? And you get another one, you get the same mistake. So that's three times you get nothing but my aggregate.
Yeah.
So the question is, how do you introduce some variety into your page and get some different solutions?
So actually, the process of introducing variety is actually pretty well understood. That's what Alina talked about, essentially, right? So for all of the root T regret algorithms, you're always both exploring and exploiting.
So can you use that kind of algorithm to accommodate adverse events?
If I understand your definition of adverse events right, the answer is yes.
Adverse events when things go wrong.
Yeah. So there's several kinds of adverse events you could think about. I guess one of them is, the reward is small. And this doesn't deal with the case when the reward is sometimes small. You need to actually map your rewards onto a unit interval, which might be non-trivial with real humans involved. But if you can do that, then...
A caveat of what he's talking about, though, sometimes one adverse event is
Yeah.
Everybody has a head bleed, that's it. Falls over.
Yeah.
So, how do you, like right.
Yeah. So well, I guess the way I would think about that is that there's, I mean, if you map that onto a reward interval, then, there's going to be a big difference between head bleed and normal, right? And there was one more question, I think. Yeah.
I have just one little comment about the early of real world data. And I really wondered, what I've seen, I wondered who the right mind is trusted.
The real world data? Yeah. So I've had a lot of experience not trusting data. And it matters a lot less. And I guess the real hope here is that, eventually we start recording things well enough that we start to trust it.
That's the key. You need to include information about what happened.
Yeah.
There's many things in the current country that are extremely difficult to overcome.
Yeah.
So many of the current policies that are in care, what doses of drugs are to be given, when to be given, when serum level samples are needed. They harem that we really
Yeah.
Those are actually valid points. And the problem, the answer to your question, who in the world would trust it, will be the next time Dr. Stenning will get out in your end. That's the data he's trusting. That's the data. As awful as we all may think it is for valid scientific observation and experimentation, that's the data that's embedded in the clinical decision making being used all the time.
that's
And
the problem.
you're,
right there.
and I absolutely agree. One of the challenges is, can you use the data that's currently being used, and perhaps the outcomes from using that data are no better than random chance. Certainly we have many examples. But the question is, what can we do with that data? And can we do anything? I mean, we could just stop right there. Don't trust it for anything. Stop the data. Unfortunately, we have to use it all the time.
Need to be done to make that data better than it can be.
But demonstrating the value of
Policy that there's this chart I thought that given my order, when it was given the half hour on when we ordered, it was dead precisely the top of the chart.
absolutely
Same
true.
thing, 55.
And the first thing we need to do, that is there are resources required to assure that the data is reported accurately and is correct data. And one has to demonstrate that there's value in doing it. That's part of it.
I don't know if any other company that accepts really such commercial data.
That's why it's called the art of it.
So clinical judgment.
So I think it's absolutely right that there needs to be a cultural change. That has happened to a large extent at Yahoo, where originally people just didn't record data very much. And, now it gets recorded a lot more. So the way to do a cultural change is incrementally. So, and you want to be changing the culture on both sides, right? So when David Hauser was talking, he said it's time for the geese to get involved. And I think that's absolutely right. And a good way to do that is to set up, take your least damaged data and set up a challenge of some sort that the machine learning people can get involved in. And that will make people aware of the problems, and it will also, when they succeed, which they will do, these prediction people are pretty good. If it's possible to succeed, they probably will. Then once they see that, once the doctors see that, then they'll start thinking more about recording data in a reasonable manner.
It's been like talking to the
Yeah.
I know the value of accurate data, and I also attended the ICU where I know when things happen, and I know what's valuable, and I read the chart, which I know I'm going to be using for data analysis, and I see values that are incomprehensible or impossible. And there they are. And I go, who put this number? A number that's 50 times what would be a normal number. That number was entered, captured, validated, and it's impossible. But if I run that through an algorithm, the algorithm may or may not. It's impossible. So,
process, noise,
and
Must be time for lunch. Sorry, David, we don't want to keep
Hey,
you.
no, it's a fascinating conversation, but let's let
Continue
people
it at lunch.
continue it at lunch. Yes, we have a shortish lunch. So.